All right, today we are cracking the code on what I think is one of the biggest moments in modern AI. We're going to dig into how this one revolutionary idea taught a computer to not just play video games, but to absolutely master them at a superhuman level, starting with nothing but pixels on a screen. Seriously. And the answer? Well, it's going to change how you think about intelligence itself.
So, here it is, the big question. How do you do it? I mean, think about it. You've got a computer that has no idea what a paddle is, or a ball, or even what points are. How in the world do you get it to become an expert at a game like Breakout? This puzzle stumped researchers for years, and the solution they came up with is nothing short of brilliant.
So, to really get the solution, we first have to understand the rules of the game. Not for the human, but for the AI itself. And this all falls under a field of machine learning called reinforcement learning.
At its heart, reinforcement learning, or RL, is a lot like training a puppy. Seriously. When the AI does something you want it to do, like hitting the ball, you give it a little treat, a positive reward. And when it misses, no treat. It just learns over and over through tons of trial and error which actions end up getting it the most treats.
Now, for this to work, you basically need three key players on the field. First, you've got the agent. That's our AI, the learner. Then you have the environment, which in this case is the Atari game itself. And finally, you have the reward, which is just the score. The AI's entire goal, its whole reason for being, is to figure out a strategy, any strategy, that gets it the highest score possible.
Okay, but here's where it gets really hard. While this whole training with treats idea works great for simple problems, classic video games, well, they presented a massive, almost impossible challenge for the AI of the time. Let me put it this way. For a super simple game like tic-tac-toe, you could, in theory, write down the best possible move for every single layout of the board. But for a game like Breakout, with the ball bouncing all over, the paddle moving, the number of possible screen combinations is just insane. A cheat sheet for that would be bigger than the known universe. No exaggeration.
And when I say insane, I mean it. We are talking about a number with 100 zeros after it. That's more possible game states than there are atoms in the entire observable universe. So yeah, the old school approach of just memorizing the best move for every situation, it was completely, totally impossible. They needed a new way to think.
The old methods had just slammed into a brick wall. The AI couldn't just memorize things anymore. It had to actually learn and generalize from what it was seeing. It needed something less like a massive cheat sheet and more like intuition.
And that huge leap forward finally came in 2015 from the researchers at DeepMind. They came up with this groundbreaking solution called the DeepQ network, or DQN for short. And that little Q in the name, it stands for quality. And believe me, it is the key to this whole thing.
This is the genius move right here. You see, that old cheat sheet idea was called a Q table. It literally stored the quality or value of every single move in every single situation. With Atari, that table was just too big. So DeepMind's idea was brilliant. What if, instead of looking up the answer, the AI could predict it? The DeepQ network uses a neural network to estimate the Q value, that quality score, for each move. It's not memorizing. It's developing an intuition for what makes a good move, just like you or I would.
So how does it actually build this intuition? Well, it follows this really simple but incredibly powerful loop. First, it sees the screen, just the raw pixels. Then its brain, the neural network, predicts the quality score for every possible action: move left, move right, or stay put. It then acts on the move that has the highest predicted score. After that, it stores that whole experience, what it saw, what it did, the reward it got, as a single memory. And finally, and this is crucial, it learns by replaying random memories to get better and better at predicting those scores.
Okay, so the first secret ingredient that makes this all work is called experience replay, and it was a total game changer. Why? Well, think about it. If an AI only learns from what it just did, it gets tunnel vision. But by storing thousands of past moments and replaying them in a completely random order, it starts to see the bigger picture. It learns the general rules of the game, not just what worked 5 seconds ago.
It's exactly like a pro quarterback reviewing plays from the entire season, not just the last one, to build a real deep understanding of the game.
The second secret ingredient is the target network. Now, this one's a little more technical, but the analogy is simple. Think of the main network as a student who's frantically trying to learn, constantly changing its answers. It can get pretty chaotic. The target network is like the answer key. The student's goal is to get its answers to match the answer key. But here's the trick. The key only gets updated every once in a while. This stable, unchanging target prevents the whole learning process from just spiraling out of control.
And what's truly amazing about all this is that this ability to learn from raw visual data wasn't just about winning video games. No way. It unlocked a massive range of real-world applications. So in robotics, DQNs are now teaching robots how to grab and move objects. Just like it learned to move a paddle to hit a ball, a robot arm can learn through trial and error in a simulation, without needing a human to program every single possible movement.
For self-driving cars, this exact same logic helps the car's AI make those split-second decisions about which path to take or how to avoid an obstacle. It learns from huge amounts of driving data to navigate really complex traffic situations. Over in the world of finance, DQN agents are learning to make buy and sell decisions. They literally treat the stock market data as a kind of game, where the only goal is to maximize the reward, which of course is financial returns.
And this is just incredible. In healthcare, DQNs are being used to help optimize treatment plans for patients. They can learn from patient data to recommend drug dosages or interventions that maximize the chances of a good outcome. It's mind-blowing.
But you know what? The story doesn't end there. The original DQN was this huge breakthrough, absolutely. But it was also just the starting point. The AI community saw what was possible and immediately started building on it.
So right away, researchers found ways to make it even better. For instance, they noticed the original AI could get a little too optimistic, overestimating how good its moves were. So they created something called double DQN to keep its predictions a bit more grounded. They also realized the AI was wasting a lot of time learning from boring, uneventful moments, so they came up with prioritized replay, which is a clever way to force the AI to focus its training on the most surprising mistakes and its biggest successes.
And really, that brings us to the most important takeaway of all. Learning to play Atari was never really about the game itself. It was a proof of concept. It showed that it was possible for an agent to learn directly from a complex, messy world, and that paved the way for the future of AI.
This entire journey started with a simple screen full of pixels and an AI that was just trying to get a high score. And now, that same core idea is tackling huge problems in robotics, medicine, and finance. It really leaves you wondering, what complex, maybe even seemingly unsolvable problem in your world could be cracked by teaching an AI how to play?